Daniel, can you confirm you can hear me?
Yes, I can hear you fine. Josh, good morning. Just started
Morning.
recording too.
Perfect. Okay. Perfect. Hello, everyone. Good morning. Thank you for joining us. My name is Josh Peters. I'm the Los Angeles Territory Sales Manager for Ponton Industries. I'll be your host today. Just a couple quick housekeeping items before we get started. You've all been muted upon entry. If you have a question or comment, please use the Q&A button on the left-hand side of your screen. I'll be monitoring that throughout the webinar today, and I'll answer any questions I can. Otherwise, we will have Steve answer any questions at the end of the webinar. We will be recording this webinar. The link will be available on our YouTube site for future viewing. We will also be sending out an email later today or tomorrow with the link as well. You can always reach out to us at the number on your screen, or you can reach us at info@pontonind.com. It's our email address. All right. For those of you who are unfamiliar with Ponton Industries, we've been a leader in instrumentation and control solutions for the last 50 years. For a majority of our lines, we cover California, Hawaii, most of Nevada. It's instrumentation, variable frequency drives, heat trace, gas analyzers, valves. We pretty much have a solution for anything. Here are a couple of our manufacturers that we represent throughout California, Hawaii, and Nevada. And I really want to just take a quick second to put a product spotlight on a couple of items that I feel go hand in hand with fluid components. One of them being Thermon. Thermon is a U.S.-based company out of Texas. I believe it's San Marcos, Texas. They manufacture heat trace and tubing bundles, extremely high-quality stuff. We stock a bunch of it here, so if you ever have an application for heat trace, please let us know. Also, Hariba. Hariba is out of Irvine, California, and they are a leader in gas analyzers, gas analytics. Their ENDA 7000 is a stack gas analyzer, huge in the for continuous emissions monitoring, extremely reliable. Please let us know if you have any opportunities for those as well. So for fluid components and Thermon, I want to take a second to say that Qcon is the representative up in Northern California. Gary and Ram, they are your contacts for Northern California. If you have an application for Thermon or fluid components, they would be your contacts. All right. Lastly, our next webinar is scheduled for May 28th. We'll be just going over pressure transmitters and their various applications. Sean McNutt, and he will be giving the presentation. He's from Siemens, and he's a process engineer from Siemens. With that, I'm going to turn it over to Steve Craig. He's a sales manager at Fluid Components International. He has a Bachelor's of Science degree from Iowa State University, and he's been with Fluid Components for 25 years in engineering and sales. All right, Steve, I'm going to turn it over to you and make you the presenter. All right, there you go, Steve.
Let's make sure he's not muted still. He might be.
All right. No, I've got it. Thanks. All right. Thanks, Josh. I appreciate that brief intro for myself. Thanks, everyone, for carving out some time today to join this session. Today, what we're going to do is go over the basics of accuracy. And there's a big difference between ideal accuracy and installed accuracy. So we're going to spend a little bit of time to make sure we're all grounded on what is the real accuracy in an installed process. We'll also go through what can affect those accuracies, such as gas flow profiles, what those are, and the disturbances and best practices. Gas flow measurement is unique. It's not like a liquid. There's thermodynamics involved, such as temperature, pressure, flow profiles. So it's very important that we understand the basics of gas flow profiles and the disturbances. And then we'll go through some of the solutions that we have available within the industry for removing any kind of issues with gas flow profiles. So let's get started with accuracy. Let's get grounded. What is accuracy? Accuracy is the degree of conformity of an indicated value to an acceptable reference standard or to an ideal value. Basically, it's hitting that bullseye. And let's understand the difference between three different levels of accuracy. One is that ideal or perfect accuracy, hitting that bullseye every single time in the middle. And then accuracy in a controlled laboratory. It's much different than when it's actually level 3, installed accuracy in the process itself. So level 1 accuracy, the ideal. It's hitting that bullseye every single time. It's an infinite center. Level 2 accuracy, attainment under laboratory conditions. Basically, you're approaching that ideal accuracy and you're maintaining that accuracy with the finest engineering tools and also based on master reference flow meters that are traceable to the National Institutes of Standards and Technology testing. Level 3, that's when you're installed. We all know that we don't always have, and in most cases don't have, an ideal installed location for gas flow meters. Here we're showing a flow meter right after a pump, or we're showing a flow meter right after an elbow and upstream from a valve. So what types of reference standards do the calibration laboratories use, and what references do customers typically use in their plant? For calibration laboratories, we're typically referencing a master flow meter that's traceable to NIST. But in the plant, we're always looking at, well, how do we verify the flow meter that's coming from the manufacturer after it's installed? A lot of times people are using stoichiometric calculation, mass and energy balance. What comes in must come out. Or blower compressor discharge curves, or control valve positionings. I know that if I set this valve at this position, this is the flow rate. And then operator experience. I've been in plants where an operator will walk up, put his hand on a pipe, and he can tell, this is about this flow rate. He's been around enough to be able to get the feel of what the flow rate should be. So that's the basics of accuracy. There's also, along with accuracy, there's repeatability. You can't really have accuracy without repeatability. So the random error, repeatability is the random error observed in a set of repeated measurements. It's the combination of stability and precision, but it can not necessarily be accurate. You can be repeatable, but not accurate. But to be accurate, you have to be repeatable. Here I'm showing a chart, and on the left-hand side, you can see that all the dots, or the majority of the dots, are located in one area. That's repeatable, but it's not in the bullseye, so it's not necessarily accurate. And then if you look at the middle chart, it's kind of accurate, but it's not repeatable because they're randomly located throughout the bullseye, or the error chart. And then on the right-hand side, we see repeatable and accurate. They're all within the bullseye, so they're repeatable and they're accurate. So when we look at process gas accuracy, thermal mass flow meters are excellent process control meters. In order to be good process control meters, repeatability has to be good. And typically with thermal mass flow meters, repeatability is 0.5% of reading, which makes it a good process control. You want to be able to set the valve. You want to be able to control process gas repeatably. Excellent repeatability is prerequisite for excellent accuracy. Poor repeatability, poor accuracy. And then if we look at accuracy as a percent of reading. Now I'm going to speak a little bit on percent of reading, and then I'm going to speak a little bit on percent of full scale. Because when we're measuring gases, typically we say something like We're 1% of reading, 0.5% of full scale. So let's take a look at what those both mean. The range reading is the range of allowable readings as a percentage of the reading at any flow rate. As an example, a meter calibrated from 20 to 200 normal cubic meters per hour with a 1% of reading accuracy. Therefore, at the maximum flow of 200 cubic meters per hour, actual flow can be anywhere between 198 or 202. And then we also take that to the minimum flow of 20 cubic meters per hour. And we're looking at, okay, now we have 1% of that. So we're 19.8 to 20.2 cubic meters per hour. And if you look at what that looks like on an accuracy chart, on a calibration verification chart, you can see it's a straight line, plus or minus 1%, from minimum flow on the left all the way up to maximum flow on the right. Now, that's reading. Let's take a look at accuracy as a percent of full scale. It's a unique type of accuracy statement. The range and full scale is the range of allowable readings as a percentage of the full scale reading. Example, a meter calibrated from 20 to 200 cubic meters per hour with 0.5% of full scale accuracy, which is pretty much a standard within the industry, is equal to plus or minus 1 cubic meter per hour at any reading. That's important to understand. So let's look at an example. At a flow rate of 200 cubic meters per hour, the actual flow can be 199 to 201. So 0.5% of 200 is 1. That's how we arrived at that range. At the lower flow rate, it's much different. It's applied much differently. So at a lower flow rate of 20 cubic meters per hour, the actual flow can be anywhere between, we take that plus or minus 1 cubic meter per hour, 19 to 21. Therefore, that percentage is much greater at the lower end. And we have a flow curve error band that encompasses more than just that straight line reading that you see in the dotted lines. So the full scale error is the lines that are nonlinear and extending out from the low flow being on the left all the way up to the maximum flow on the right, and the inaccuracy statement on the left-hand side. So let's take a look. Accuracy of reading versus percent of full scale. How does it actually look? So if we're looking at a flow rate of 100, plus or minus 1% of reading would be 99 to 101. Plus or minus 1% of full scale, same thing, 99 to 101. Equivalent to the reading. Let's look at the lower flow rate of 10. It now has plus or minus 1% of reading, so it's 9.9 to 10.1. But if you look at the full scale, it's equivalent to 10% of the reading. So it's 9 to 11. And we'll work through some formulas so that you get an idea of how that's actually calculated. And then if we go to the minimum flow of 1, we have 1% of reading equals 0.99 range to 1.01 range. If we look at the full scale, it can be anywhere from 0 to 2, which is 100% of the reading accuracy statement. So this is a busy page, but I wanted to include this and work through it so everyone understands how to calculate the accuracy statement from the manufacturer. When we say we're 1% of reading, 0.5% of full scale, how does that actually look? So a meter that's calibrated, and we'll use again the flow range of 20 to 200 cubic meters per hour with a 1% of reading and 0.5% of full scale accuracy. How is that calculated? So first we calculate the full scale error. And we know that's 0.5% times 200 which is equivalent to plus or minus 1 cubic meter per hour at the maximum flow and the minimum flow. Then we calculate and blend in the reading error of 1%. So at the maximum flow rate, 200 cubic meters per hour, actual process flow error can be plus or minus 1 cubic meter per hour, full scale. We calculated that in item 1, plus 200 times 1% of reading, which is equal to 2%, 2% plus 1%, which actually turns out to be plus or minus 3 cubic meters per hour, and therefore the error for the flow range is 197 to 203. And at the minimum flow rate, that increases dramatically. So if we have 20 cubic meters per hour, we know that full scale error is plus or minus 1 cubic meter per hour, plus 20 times 1% of reading, which is 0.2%, so 0.2% plus 1%, which is equivalent to plus or minus 1.2 normal cubic meters per hour. Therefore, we have calculated what that flow range would be. If you look at a curve, and that's how it comes down to. At the maximum flow, if we have 1% of reading, 0.5% of full scale, it's whichever one is larger. So the full scale reading at the high end is not even playing a part in the accuracy statement. But at the lower end, the full scale reading is actually what the accuracy statement is for that flow meter. That's how we're looking at accuracy with regards to reading as regards to full scale. Now, what is turndown? Because I'm bringing up turndown because that affects that full scale accuracy. Turndown is the ratio between the minimum and maximum flow rate. An example, a calibrated range of 10 to 100 cubic meters per hour has a turndown 10 to 1. 100 divided by 10 is 10. So it has a 10 to 1 turndown. And note, there is no flow meter that can read zero flow. So when we talk about minimum flow, some specifications will come out and say, okay, we want flow from 0 to 100. Well, we know that we're not going to be able to read zero flow. There's always a cutoff at the 4 milliamps, and that 4 milliamps is never zero. So we look at thermal mass flow meter technology, and it has at least a 100 to 1 turndown. That's one of the benefits to thermal mass flow meters, having that large turndown. There's very few technologies that can get up to that 100 to 1 turndown. Some thermal mass flow meter manufacturers have up to 1,000 to 1 turndown. This becomes more critical, that large turndown, when we're starting up a plant and then going into the normal process, and then let's say we're on a flare gas where all of a sudden we have an upset or a blowdown going on in the process. We want to be able to read all of that. And it also goes for boiler plants. Let's say we're measuring primary air to a boiler. On startup, we're at low flow. When we get up to the process flow, it's at a larger flow. So we need that larger turndown to be able to provide safety for plant startup. To give you an idea of other gas flow meter technology turndowns, orifice plate is typically 4 to 1. A turbine meter, 10 to 1. Vortex, 12 to 1. Sometimes I've seen them 14 to 1. Ultrasonic transit time is typically 400 to 1. So it kind of gives you an idea of what thermal mass flow meter technology can bring for your application. And then I was mentioning that I brought up turndown because it does affect the accuracy. Accuracy at low flow is better with a lower turndown because of the way that it's calculated. Example, flow meter accuracy is plus or minus 1% of reading, 0.5% of full scale. If calibrated 10 to 100 normal cubic meters per hour, minimum flow accuracy is 0.6 cubic meters per hour, which is equal to a flow range accuracy statement of 9.4 to 10.6 cubic meters per hour, which is about 6%. If we look at a larger turndown, 1,000 to 1 or 100 to 1, where we're going from 10 to 1,000 cubic meters per hour, minimum flow accuracy is plus or minus 5.1 cubic meters per hour. So therefore, our low end accuracy range has increased significantly. So Turndown plays a factor in what the accuracy of the instrument is. It's very important to understand that. One thing to note is FCI is the only manufacturer that provides an accuracy statement that is 1% of reading, 0.5% of full scale, with a maximum inaccuracy of 5%. So we cut off that full scale error down at the low end to 5% only. That's the worst error that the flow meter can have. So calibration labs, they're important because thermal mass flow meters are all calibrated at the factory before they're delivered and installed. So the calibration lab becomes important. What kind of manufacturer has the calibration lab? What kind of metrology program do they have? It's important to understand if this is a recognized calibration test facility and that they have NIST traceable master reference flow meters. To give you an idea, it's always interesting. People want to know, well, if you have a calibration test facility, where do you stand on that chronological order from the master flow meter? The National Institute of Standards and Technologies, CC is what we use. That's a laboratory located in Colorado. They have a master meter, and it's a bell prover or a sonic nozzle. Okay, their bell prover and sonic nozzle are actually based back to that National Institute of Standards and Technology. So we see the chart as it goes down, and then that bell prover and sonic nozzle from CC goes to a transfer standard. And that transfer standard is what they're using to verify the calibration of the manufacturer's test master meter. And so we get to where FCI in our calibration laboratory, we go back and use that transfer standard to verify our master flow meter calibration. And then what we use in our factory is a variety of different master meters. It depends on the type of, if it's a gas flow meter, if we're calibrating in gas, high flow rate, what the turndown is. But we're using sonic nozzles that have a metrology back to CC. Turbine meters, same thing. Rotometers, that's our master meter. And then that master meter is actually calibrating our flow meters. So that's a hierarchy of the metrology in a calibration test facility. So in summary, the installed accuracy can be verified by the customer's reference standard. It can be, we went through and talked about stoichiometric, what comes in must come out. It can be just, I know that I set the valve at a certain position. And so when we're talking about accuracy and it becomes more important, then we have to agree on what is the reference standard. What is the end user using? What is the customer using to come to an agreement on what the accuracy of the instrument is? Because we know that the ideal conditions in a flow lab are not the same as what's in the process. So questions to assure satisfaction with instrument accuracy. This is something that we have to understand is when selecting the type of flow meter that you want to use. What is the accuracy or repeatability requirement? Is this process control and you're more concerned about repeatability, setting a control valve every time in the process, or are you more concerned with accuracy, efficiency of a process? And then what is the pipe or duct size? That plays a part in accuracy also, and I'll discuss that a little bit later. And then where is the probe going to be located? Which brings up the topic of how much pipe straight run is available. Typically in the industry, it's a standard of 10 pipe diameters of straight run, no obstructions, upstream from the flow meter, and 5 pipe diameters downstream with no obstructions. But in a lot of cases, and you saw some of those pictures, that's not the case. So we need to understand what the straight run is in the application. And then, is there a reference meter or blower measurement? A lot of times I'll get a call and they'll say, okay, well, the blower curve is stating such and such. But in looking at the blower curve, it's an actual cubic meters per hour. With thermal mass flow meters, the technology is mass. Therefore, it's a normal cubic meters per hour. It changes with temperature and pressure. And actual does not take into account changes in temperature and pressure. Therefore, that can affect what the blower will actually read compared to the flow meter. And then, is a flow conditioner required because of lack of pipe straight run? We'll talk about that a little bit later too, or multiple sensing points, averaging flow meters, and we'll talk about that also. And then calibration considerations. It's important to understand, and this is something that's overlooked many times, is if we are in a digester gas, is that meter calibrated to that gas composition, or is it air calibrated with an equivalency added to it based on that gas composition? Most manufacturers only perform calibrations in air. One of the unique features of FCI is that we have a very large calibration facility, over 20 calibration test stands, and some of them dedicated to strict actual gas calibrations. The actual gas calibration is a much higher accuracy calibration than an air equivalency. And then, is in-situ calibration required if in a large pipe diameter greater than 18 or 24 inch? In-situ field calibration can be performed, typically used with a Pitot tube, where we traverse the inside of that pipe or duct, and we understand what the flow profile looks like on the inside of it. And again, I'll discuss that a little bit later. And then, what reference standard is used to verify the accuracy? So let's look at, gas is unique. It's different than liquids. It has flow profiles and disturbances that affect the accuracy of the instrument, and pressure and temperature. So what are some of the best practices? Let's review recommended flow meter installation. Let's first get grounded on what is the recommendation for the meter installation, types of gas flow profile distortions, and typical gas flow disturbances. And then what are the solutions available to you that can overcome some of these things? So, typical installation of a point measurement doesn't necessarily need to be thermal mass. This is any single point flow meter, is that we locate the sensor at the center line of the pipe. And we have enough straight run upstream to the flow meter, 10 diameters, and then 5 pipe diameters downstream before any kind of elbow or valve. And typically, the way that we approach when we look at and size different applications, it's really dependent on the pipe diameter. So, and that's based on the flow profile that's created based on the pipe diameter. And typically, an 18-inch or smaller, we have a fully developed turbulent flow profile where the velocity, maximum velocity, is more at the center line of the pipe. The pipe wall is creating friction and slowing down the velocity alongside the walls. So therefore, at the center line, we have a much higher velocity. And this is what we calibrate to for flow meters that are 18-inch and smaller line sizes. But when we go into applications where the pipe diameter is greater than 18 inches, a pipe or duct that's greater than 18 inches typically has more of a flat flow profile. whereby the velocity is relatively uniform across the cross-sectional area of that pipe, where the friction of the wall has less effect on that flow profile. So what are some of the typical gas flow distortions out there? We're looking at like 3 types. Flow profile distortion. It can be a T, an elbow, a gate valve, a damper. It can be any number of things that really distorts that flow profile, where the maximum velocity is not necessarily at the center line of the pipe. We have to be concerned about that if we don't have enough straight run. And then we can also have swirl. Swirl can be when we have 2 elbows out of plane, and it's creating a swirl on the inside of that pipe of that gas. And it can also be in a stack. Typical stack gas has a lot of swirl in it. And then we have to look at Reynolds number transition. Reynolds number transition is, again, something that people don't typically look at, and it occurs at a lower flow rate. So I think we all understand flow profiles, how elbows and gate valves can affect flow profile, but let's take a deeper look at Reynolds number transition. At a low flow, especially in smaller pipe diameters, Reynolds number transition occurs. What that is, at the lower flow, we have a Reynolds number that below 2000. That's a number assigned for Reynolds. And with that, we have a laminar flow. Up in the upper left-hand corner, you see it's more bullet shaped, where the maximum velocity is at very high at the center line. But as flow begins to increase, we go from that higher velocity at the center line to more of a fully developed turbulent flow profile, which is on the right-hand side. But there's a transition where that occurs. And that transition between laminar to turbulent is between 2,000 and 4,000 Reynolds number. So it's important that the manufacturer has a sizing software program that analyzes that gas and provides the Reynolds number for that gas to confirm, is this occurring in your process? The reason why I bring that up, because in that transition, it affects the reading of the flow meter. And with every application, we look at that Reynolds number. This is a for instance. So this is a calibration, a linear or nonlinear calibration chart. And what it shows is from left to right on the bottom is increasing flow. From bottom to top on the left-hand side, it's showing that delta R, or that difference in resistance in our sensor. As flow increases, that difference in resistance decreases. So we're looking at this nonlinear relationship. If we go from a low flow, and you can see in the blue line, which is just to the left of the purple line, without Vortab, you can see where that flow begins to increase and that delta R, that change in resistance, begins to decrease. And then all of a sudden we go through this transition period where we're going from laminar flow to turbulent flow. And what that does is going from that bullet shaped to more of a flat flow profile, it's actually showing that we're decreasing flow, where that blue line all of a sudden begins to go up after 0.5 standard cubic feet per minute. That's very important to understand. Now all of a sudden we're increasing, and we are actually increasing, but during that transition, we're showing that we're decreasing flow, indicated flow. Therefore, we have to provide some sort of flow conditioner to remove that transition. And what FCI recommends is a flow conditioner that basically from the very low flow all the way through the transition provides a repeatable and known flow profile. It removes the error from that Reynolds number transition. Some of the types of installations I highly recommend a retractable packing gland assembly. What this does is it allows you to remove the flow meter from the process without actually shutting the process down. And so if you look at the bottom left hand, we have the flow meter. It has a packing gland on the probe. The packing gland is flanged, and it's flanged process connection with an isolation ball valve. So the flow meter is inserted through the ball valve and into the process. To remove the flow meter probe, you just loosen the packing gland nut, which is on top of the packing gland, which is attached to the probe. Then you pull the probe up in step 2 through the ball valve until it clicks into the packing gland. And then you close the ball valve. And then step 4, you remove the process from the probe from the process connection. You never have to shut down the process. It's relatively inexpensive, and it's a great added feature to any thermal mass flow meter. And it's one of the benefits that a single point insertion type flow meter has. And then let's look at best practices, such as, I'm taking an example such as digester gas. It's important to understand that digester gas can be very wet, and it can have a lot of fouling media in it. Constant power, there are basically 2 types of technology in thermal mass flow meters. Constant power, which adds a high heat to the active RTD, and then it watches that difference in resistance as flow increases as that active RTD is cooled. And there is also constant temperature. There's advantages and disadvantages to both. Constant temperature, it happens to be very fast response. Constant power tends to be a little bit slower response. FCI happens to offer both technologies, and we use them for different types of applications. Constant power with that higher temperature, though, is great in digester gas, fouling gas, flare gas, anywhere you're going to have problems with clogging that sensor. Because that sensor, that active RTD, the sensing element itself, the one that's being cooled by the process gas, is actually staying clean because it's not allowing the condensate to build up on it. Because that higher temperature keeps the dew point of the gas, it keeps the thermal well higher than the dew point of the gas. It doesn't allow that condensate to build up on it. And this picture shows a good reference with regards to the bottom thermal well on that sensor is clean. The reference, it has the heat added to it. The top thermal well and RTD is the reference. It's in at the process gas, and you can see how it's accumulating that debris on it. But that's not the sensing element. The sensing element's that active one. That's the one you need to keep clean. And one installation note, if you do have water vapor that's going to condensate in the pipe, if you're draining water out of your process and you know you've got water condensating inside it, we highly recommend, as a best practice on installation, is coming in 45 degrees from the side mount the flow meter. Do not put it in from the top, because what happens is that water vapor in that gas will condensate on the probe and drip down the probe and onto the sensor itself. And you don't want that water on the sensor. That's what we're trying to do, is keep it off the sensor. So it's important that we come in from the side, or as better yet, 45 degrees from bottom. Therefore, any moisture or condensate that builds up on a probe does not run down onto the sensor itself. So let's look at what we have available. If we know that we are going into a very wet gas, and we know that we're going to have condensate, and we may not have the best ideal situation, but basically we have water entrained in the gas, where the water droplets are being carried in the gas. Even the best constant power technology may have an issue with that. Therefore, FCI has a solution, and it's called a moisture shield, whereby you can see on the upper left-hand corner where we have our sensor located in a shroud. We have an inlet with a screen mesh. The gas passes into that screen mesh, and then to the right goes into the sensor, which you can see on the bottom, which is the outlet center, and then out that side. This moisture shield collects any water droplets and knocks it out of the gas stream, so the sensor never actually sees that water droplet. And of course, we do have water drain outlets on the moisture shield, so the water that's accumulating from that shield or from that mesh is actually being drained out. And then let's talk about some cases where what we don't want for an installation. This is important. I enjoy this picture on the left. It's showing where we have an inline flow meter, and you can see the conduit port butted right up against the wall. They installed the flow meter correctly because we had a flow from, if you can see it, from right to left, and the flow meter is calibrated right to left, so therefore they installed it correct, but the design engineer or the person that was working on this forgot that they had the conduit port pointed to the wall. It's just a heads up, something to always keep in the back of your mind when you're ordering or working with a flow meter. And then another one is installing the flow meter with the correct flow direction. And it's important because on the sensor, on the probe itself, near the housing, there's a flat. And that flat has an arrow saying flow this direction. So that flat needs to be parallel to flow. The picture on the right, and you can see the flow probes are just randomly installed. They did not look at the flat to ensure that it was parallel to flow, because at the bottom where the flow meters are installed, you can see the pipe, and the pipe is left to right flow. That induces error or inaccuracy of the flow meter when it's not installed parallel to flow. And then another one, erosion. It can be like from cement or any kind of highly erosive material or debris that's in the gas or airflow measurement can erode the probe. If that's the case, there is a solution. And what we do is we add a chromium carbide coating to the wetted material, which reduces significantly the erosion from that material. And then on the right, we have corrosion. And this one's showing corrosion damage due to H2S. For these types of applications, we recommend a different type of wetted material, such as Hastelloy C. Of course, you would have a better idea as far as what works in your process connection, and we would entertain that. And then we're looking at compression fittings. Be careful with, there is a process connection. It can be fixed threaded. It can be a compression fitting. It can be flanged. If it's a compression fitting, there are different manufacturers of compression fitting that are offered on flow meters. Typically, we use a Teflon compression fitting, Teflon ferrule. That allows for the compression fitting to be loosened and tightened many times. But when we get into a higher temperature process, it requires a metal ferrule. With the metal ferrule, it's important to remember that it's a one-time lock-in. Once you've installed it and you've tightened that and you've crimped that metal ferrule, you cannot remove it and then put it back in because you've damaged that seal with the probe. And then conduit ports. Again, I showed you this picture earlier, but it's important to note this is a great installation. I love it because it's coming in from 45 degrees from bottom. And actually in this application, they're draining 20 liters per hour of water out of here, and the flow meter is working fine. The problem is they pointed the conduit connection up. What this does is it allows susceptibility to water leaking into the enclosure. Even with the world's greatest cable glands, it's going to happen. So always try to mention that the conduit port has to be pointed down. And then let's talk about larger pipe diameters, which we're talking about multi-point averaging transmitters with single point probes. We're looking at ducts that are larger, or pipes larger than 18 inches, whereby we're using multiple sensing points to average back to one transmitter. And the way that when we locate those sensors in a pipe or duct is we're using equal area, meaning area 1, shown on the left, is equal to the area of 2. So therefore, we locate that sensor between those two areas. And same with a 4-point system. And that's the same with a rectangular duct. We're just dividing up the area within the duct to be representative of the area of that duct. So with 1 point, we know exactly to put it in the center. 2 points, we divide that by 2 and put each point in the center of that area, and so forth. And then another option or solution is, in these larger pipes or ducts, is a Pitot tube in-situ field verification and calibration. What that allows us to do is take a Pitot tube, typically an S-type, and up in the upper right-hand corner, you see the person inserting the Pitot tube in a Pitot tube test port. And we stick that Pitot tube in there, and we traverse the inside of that duct to understand what the flow profile looks like, and also take that DP flow measurement and make it either verify the calibration of the flow meter is correct, or make corrections to the flow meter, thermal mass flow meter, based on that traverse data. And typically when we get into these larger pipes and ducts, the flow profiles are very erratic. We will calibrate to a flat flow profile, insert the flow meter into it, and then we'll do this Pitot tube traverse. What it also allows is you can verify third-party instrument what that thermal mass flow meter is reading correctly. And then flow conditioners. There's a variety of different flow conditioners. What they are doing is they're reshaping the flow profile to a consistent, repeatable flow profile. We have tab types, we have perforated plates, we have vane, we have tube bundles. FCI happens to offer meter run type flow conditioners, where it's a spool piece or an insertion with the flow meter actually process connection installed on it, and you just drop it into place. And we have some that are, you can have a flow meter right after an elbow, 3 pipe diameters downstream from an elbow. So we install the flow conditioner in the elbow itself. And then we have a very inexpensive flow conditioner. It's a panel type. And what this has done is it's sandwiched between 2 flanges, and it allows for conditioning the flow. It's lightweight and easy to install. Typical flow conditioner straight runs require 3 pipe diameters to the flow conditioner, and then 3 pipe diameters from the flow conditioner to the flow meter itself. To give you an idea, this is a busy chart, so I'll let you soak it in for a moment, but what we're doing is, if you take the dark blue line on the left-hand side, it says % of error. On the bottom, it says flow, standard feet per second. So decreasing flow to increasing flow. And the percent of error. The blue line you can see is a FCI flow meter that's calibrated and verified, and that's the error rate of the flow meter itself, with plenty of straight run. But if we insert a gate valve 6 pipe diameters upstream, you can see that light blue line at the very top. And you can see how that adds an inaccuracy anywhere between 5 all the way up to 14% along that line. And it depends on what the disturbance is, how much inaccuracy it induces on the flow meter, as based on this chart. But if we put a flow conditioner in there, we remove that disturbances effect on the flow meter. And this is showing how it brings all those inaccuracies within the stated accuracy of the flow instrument itself. I want to thank you for your time. I'm open for questions, and I'll turn this back over to Josh.
All right, Steve, we got a couple questions. Question number 1, can you only rotate the head of the transmitter?
No, you cannot. You mean the enclosure itself? No, you cannot. We do have the display that's rotatable, but not the actual enclosure itself.
What is the typical flow profile in a rectangular duct with regards to the Reynolds number?
The Reynolds numbers are more in effect at the low flows in the small pipe diameters. When I say pipe diameter, I'm talking 2-inch and smaller. Typically, when we get larger than that, we don't see that Reynolds number. We're always above that 4,000 Reynolds number.
And then our last question we had is, why are the electronics not potted to prevent moisture intrusion?
Why are the electronics not potted for moisture intrusion? We do put a coating on the electronics to try to eliminate moisture within the enclosure. The typical damage that occurs to the electronics is when we have a leakage through a conduit port, through a cable gland.
Perfect. Yeah, via the conduit. Let's see what else we got. What is the increase in pressure drop due to the flow conditioners?
Very good question. Of course, it depends on the velocity of the flow and the pipe diameter. But typically, we're talking about anywhere between 2 to 10 inches of water column. So it's relatively low. But it is a problem in such cases where you've got flare gas or extremely low flows. You have to be very careful with the pressure drop. But typically, it's between 2 to 10 inches of water.
Do we have a field bus model?
Yes, FCI does offer field bus. We offer it H1, and we're verified through ABB, Emerson, so it is H1. We also provide Profibus PA, Profibus DP, HART, Ethernet. Yes.
When a FCV is present, is there a preference to position the flow element upstream of the FCV to avoid error or downstream?
I'm not sure I understand that question. What is SPV?
Will you please write in, explain what FCV represents, and then I'll go on to the next question and come back. The next question was, how much flow sensor direction affects the flow element or flow measurement? Because perfect alignment of sensor is very difficult to be performed.
I agree.
So how much?
I agree. Yeah, that's kind of a double question. One is the alignment parallel to flow. How critical is that? If you're within 5%, typically you can eyeball getting that in, and it's not going to affect accuracy.
Okay.
If you're rotating and you go more than 5 degrees in one direction or the other, it's going to begin to affect accuracy at a rate of, let's say, 1% up to, from 5 to 10 degrees. Now, with flow direction, if it's installed with calibrated flow from, let's say, left to right, and you change and install the flow meter from right to left, but it was calibrated the opposite direction, it can induce up to 1% error.
Okay. For our previous question, so it's a flow control valve. When a flow control valve is present, is there a preference to position the flow element upstream of the flow control valve, or to avoid error, or downstream?
Yeah, that brings up a very good point. Do you see my screen?
Yes.
All right, very good. I kept this on as a hidden slide, and it's effects of straight run. It can be anywhere from, let's say, a gate valve. Let's take a look at this. You know, when we're talking about effects of straight run, we look at it from 6-inch diameter and smaller, which is that top graphic, and then the bottom graphic, less than 6 inches, okay? I mean, greater than 6 inches, because that affects what the disturbance affects the accuracy. So let's take, for instance, gate valve. You know, the industry standard is 10 pipe diameters of straight run upstream and 5 pipe diameters of straight run downstream. What that industry standard says is for 85% of all disturbances, that's good enough. But for that other 15%, such as a gate valve or FCV, it's different. Let's take a look at this gate valve, and we're in a larger than 6-inch pipe diameter. So let's look at that bottom chart, and you can see where with a gate valve, we have to go all the way up to 15 pipe diameters for that gate valve in order to not induce any more inaccuracy on the flow. Now, this is available on our website if people want to download it, but we also have a sizing software program that Ponton uses when discussing the effects of straight run.
All right. What are programs for training technicians on effective verification of installed systems?
State that one more time, I'm sorry.
What are programs for training technicians on effective verification of installed systems? Does FCI have any training or to verify their installed systems?
Yes, we do. We have trained technicians that can go in and, depending on what's going on, typically, again, we're using a reference third-party flow meter to go in and verify that. And these trained technicians can also provide training at the site on how to do it themselves, and also provide troubleshooting training.
Next question. Are inline silencer assemblies considered as part of the straight run?
Yes, they are. The picture that I showed earlier with the spool piece for that smaller 2-inch and smaller pipe diameter, you know, the spool piece is 9 pipe diameters long, and that is considered part of the straight run. Very good question.
All right, next question. If I had 2 flare lines, one high and one low, is there a way to have one probe and head configure to be a spare for either or do you have to have 2 spares? Yeah,
very good question. We actually have a model that's called an ST100, and it has options for calibrations, up to 5 different calibrations, and also options for process flow parameters. So when we provide an HP and LP flare, typically the customer wants a spare electronics, so we can actually set up the electronics for both flow meters. So therefore, you would either select Cal 1 or you'd select Cal 2.
For small tubing such as half-inch, can the electronics be remotely located? What is the length of the flow meter body?
Okay, yeah, the spool piece is 9 pipe diameters, and yes, the transmitter can be remotely located up to 900 feet.
All right. Insertion of the probe all the way inside the pipe and pulling it from the pipe half of the ID, could it be a good installation for flow element?
Say that one more time, I'm sorry.
So I guess inserting the probe all the way to the end of the pipe and then retracting it, is that a good way to find the middle of the pipe?
Actually, the probe has graduation marks, measurement graduation, meaning that it's marked in inches and metric. So if you have a 6-inch pipe, you only need to know what is the nozzle height, and you can add 3 inches, and then we like to go half an inch past center line. So half inch plus the half-inch pipe ID plus the nozzle, let's say it's flanged at 6-inch. So therefore, we know that we need to go 9.5 inches. On the probe, you can either take a marker or mark 9.5 inches and stick it down to that mark.
Do you know the effective turndown of a Venturi tube?
Venturi is typically, I believe, 8-to-1 or 10-to-1.
All right. Can flow direction be calibrated in either direction, or can it be reversed by the installer?
Yes, we can calibrate in either flow direction because we do have multiple calibration groups available. The error induced, again, is up to 1% if the flow direction does change.
All right, looks like that was our last question. So I really appreciate it, Steve. Thank you for taking your time today, and thank you everybody else who joined us. We'll send out an email later today with a recording of this webinar. Please feel free to email us if you have any other questions. Thank you.